As an aid to understanding the frequency response of transfer functions, we'll spend this presentation talking about some operations on complex numbers. Specifically, we'll look at the magnitude and phase of complex numbers, and then we'll examine the magnitude and phase of products of complex numbers and of ratios of complex numbers. The first question we need to answer is, what do we mean by the magnitude and phase of a complex number? The magnitude and phase of a complex number are very simply defined. So let's start off with a complex number we'll call C, and it's equal to a plus bj, where j is the square root of -1. A is the real part of this complex number, and b is the imaginary part. And we can draw this complex number in a complex plane. It has a component a along the real axis and b along the imaginary axis. The magnitude of the complex number c is the length of the vector c in the complex plane. So that's easy enough to find. We simply find the square root of a squared plus b squared. Note that our symbol for the magnitude of a complex number is to put braces around the complex number. Now that we've defined the magnitude, let's look at the phase. The phase of a complex number is the angle of the complex number in the complex plane. The angle that's made between the complex number vector and the real axis. This is labeled here as phi. And we can find that angle by taking the arctangent of b over a. The notation for the phase of a complex number is the angle bracket next to the complex number. It should be pointed out that there's an ambiguity in determining the phase angle when using the arctan function. The arctan function returns an angle between minus pi over 2 and pi over 2. The phase of c, however, phi, can be anywhere from minus pi to pi. This ambiguity has to be resolved by examining what quadrant the c vector is in. To do this, we only need to examine the sign of the real part, that is a. So here are the formulas for resolving the ambiguity of phase angle. Phi is equal to the arctan of b over a if a is positive. Phi is equal to pi plus the arctan of b over a if a is negative. Now, if you find out that the real part a is 0, then the angle has to either be pi over 2 or minus pi over 2. It'll be pi over 2 if b is greater than 0, and it'll be minus pi over 2 if b is less than 0. If both a and b are equal to 0, the phase angle is indeterminate. So now that we've tackled the definition of the magnitude and phase of complex numbers, let's now move on to our next question, which is, how do we calculate the magnitude and phase of the product and quotients of complex numbers? This is actually easy to do. Let's start off with the product rule. Let C1 and C2 be two complex numbers, and we'll say the magnitude of C1 is M1 and the magnitude of C2 is M2. The phase of C1 will denote phi1, and the phase of C2 will denote phi2. Now we'll take the product of these two complex numbers. So let C equal C1 multiplied by C2. Then the magnitude of this new complex number C will be equal to the product of the magnitudes of C1 and C2. That is, it will be M1 times M2. And the phase of this complex number C will be equal to the phase of C1 plus the phase of C2. That is, phi1 plus phi2. So our product rule is simple. To find the magnitude of the product, we simply multiply the magnitudes. And to find the phase of the product, we simply add the phases. Let's do a quick example to illustrate the product rule. So we have two complex numbers, C1 and C2. C1 is 3 plus 4j, and C2 is 1 minus 2j. C1 is in the first quadrant, and C2 is in the fourth quadrant. We'll find the magnitudes of these two complex numbers. So m1 is 5 and m2 is square root of 5. And then we'll find the phases. Phi1 will be the arctangent of 4 over 3, which is 53.1 degrees, and Phi2 will be the arctan of minus 2 over 1, which is minus 63.4 degrees. We don't have any problem here with phase ambiguity because we're working in the first and fourth quadrant. So here I've summarized these results for our two complex numbers. And at the bottom, I'll multiply the complex number C1 times C2. So that's 3 plus 4j multiplied by 1 minus 2j. Expanding that product out and simplifying, I find their product is equal to 11 minus 2j. I'll now use the product rule to find the magnitude and phase of the complex number C. So the magnitude of C is the product of the magnitudes. So that's 5 times square root of 5. And the phase of C is the sum of the phases. So that's Phi1 plus Phi2, which is equal to minus 10.3 degrees. We'll now check the answers provided by the product rule by directly finding the magnitude and phase of the product. So we found that C was 11 minus 2j. We'll find the magnitude of C as the square root of 11 squared plus 2 squared, and that will be 5 square root of 5, just as we found using the product rule. And the angle of C will be the arctan of minus 2 over 11, which is minus 10.3 degrees. That too checks with the answer from our product rule. Let's now look at the quotient rule for complex numbers. So let's suppose we have two complex numbers, C1 and C2, and we find their ratio, C, as C1 over C2. Now we wish to find the magnitude and phase of C from the magnitude and phases of C1 and C2. To do this, of course, we have to assume that C2 is not equal to 0. We can't divide by 0. In this case, the magnitude of complex number C, the ratio of C1 over C2, is going to be m1 over m2. So to find the magnitude of C, we simply take the ratio of the magnitudes. Then, to find the phase angle of C, we simply have to subtract the phase of the denominator complex number from the phase of the numerator complex number. So we write that as Phi1 minus Phi2. We can summarize the quotient rule by saying we take the ratio of magnitudes to find the magnitude and the difference of angles to find the phase. We'll do a quick example to illustrate, and here we use the exact same complex numbers that we used in our previous example. So C1 is 3 plus 4j and C2 is 1 minus 2j, and we found the magnitudes and phases of these complex numbers before. So now, using our quotient rule, we find the magnitude of C is m1 over m2, which is 5 over square root of 5, which of course is square root of 5. And the angle of complex number C will be Phi1 minus Phi2, and this will be 116.5 degrees. As we'll see in upcoming presentations, the product and quotient rules will turn out to be very important in evaluating the frequency response of linear time invariant systems. Now I'd like to turn to the use of the product and quotient rules in the evaluation of the magnitude and phase of a transfer function at a particular frequency. Let me illustrate the ideas through an example. So suppose you had the transfer function g of s, which was s minus 1 divided by s plus 3 times s plus 12. We want to evaluate the magnitude and phase of this transfer function at s equals 4j. Now, to find the answer, we're going to substitute 4j for s everywhere in this expression. And then the numerator and denominator will consist of complex numbers. So we'll label 4j minus 1 in the numerator as C1, and 4j plus 3 in the denominator as C2. and 4j plus 12 in the denominator as C3. So the transfer function g of s evaluated at s equals 4j is equal to C1 divided by C2 times C3. Now we'll find the magnitudes and phases of C1, C2, and C3. And those answers are shown here. Now we'll evaluate the magnitude of g at s equals 4j. And that magnitude will be m1 divided by m2 times m3, where m1, m2, and m3 are the magnitudes of C1, C2, and C3. And the answer here is 0.0651. Now let's compute the phase of g evaluated at 4j. And it will be phi1 minus phi2 minus phi3. We subtract the phases of the denominator complex numbers from the phase of the numerator complex number. The answer will be 32.48 degrees. So the transfer function g, evaluated at s equals 4j, is a complex number with magnitude 0.0651 and phase angle 32.48 degrees. And we can draw this in the complex plane as shown here. We can find the real and imaginary parts of this complex number. All we have to do is take the cosine of the phase angle and multiply it by the magnitude in order to find the real part, and the sine of the phase angle multiplied by the magnitude to find the imaginary part. So g of 4j is equal to 0.0549 plus 0.0350j. I'd like to make something clear about units of these complex numbers. We have two different complex numbers in this problem. We have values of s and we have values of g of s. For example, in the problem we were just doing, s was equal to 4j and g of 4j was equal to 0.0549 plus 0.0350j. So we've got the values of s and the values of g of s. The complex numbers that are the values of s will have units of frequency, that is, rads per second. The complex numbers that are produced when we plug in a value of s into g of s, those complex numbers have units determined by the input and output signals. So for example, if the input had units of volts and the output had units of degrees Celsius, then the transfer function would have units of degrees Celsius per volt. Now it may seem in this example like I'm just doing a lot of computation, but actually I'm trying to introduce an important idea. The important idea is that transfer functions act to change one complex number into another complex number. So if I have a transfer function g of s and I plug in s equals 4j, the transfer function then produces another complex number. It takes in one complex number as its argument and generates another complex number. We can represent this important idea in the following picture. We have s, which takes on values in the complex plane, for example, 4j. That number then goes into g of s and produces another complex number, which takes on value in a different complex plane. The first complex plane has units of radians per second, and the second one has units determined by the input and output signals. You can view g of s as a mapping of one complex number into another complex number. It turns out this idea of the mapping of one complex number into another complex number is a very important idea in much of what we do later.